Thank you very much for joining me today. I want to continue our content on the ROHM Generation 4 Silicon Carbide MOSFET. Hopefully you've seen some of our content already, including the deep dive technical review we did a few weeks ago. That's freely available on our public website. I want to show you a little bit more today about how this seemingly simple advance in technology could actually be the first step in a new revolution of power semiconductor devices. And we're going to look at this device more in context of the broader market, how this device fits in, and also take a little bit of a deeper look into the process flow and how this device is made up. So I'm joined today by my former colleague and good friend to TechInsights, Professor Peter Gammon. Hi, Peter.
Hi, Steve. Thanks for having me. It's been fun working on these devices with you. I'll introduce myself. I'm a professor of power electronics at the University of Warwick, and I also set up a consultancy company last year called PGC Consultancy so that I could do work with the likes of TechInsights and the wider semiconductor market. And we at PGC do a whole range of things related to silicon carbide and wider power electronics semiconductor devices. So we can provide testing and qualification services for silicon carbide products. We're all experts on the design and development of silicon carbide devices. We provide reporting and commentary on the supply chain. And we also do an awful lot of education and communication as regards silicon carbide power devices and the wider power electronics field. So that's the company, and as part of this, we've been working with TechInsights on these ROHM Gen 4 devices.
Awesome. Thanks again for being here today. So let's kick off with what I've called the state of play. So you'll see a big table with a lot of figures there, which we'll dive into a bit deeper in a moment. But first, there's a nice graphical representation on the right of this slide. And we can kind of see, first of all, the benefits in general that silicon carbide gives. So you see at the top, the yellow star devices there. Those are some of the latest silicon superjunction MOSFETs that we've analyzed at TechInsights. So a 650 volt device from onsemi and an 800 volt device from ST. Now, first thing you'll notice is the specific on resistance dips slightly below the conventional 1D limit. This is expected from a superjunction device. But the other thing that's worth noting is, the onsemi one, the lowest one we've seen to date, I think is around 12 milliohm centimeters squared. Now, if you're looking at what silicon carbide can do today, you're almost an order of magnitude better. So it's worth bearing that in mind, and that's where we are today in terms of silicon carbide and its advantages over silicon. Obviously, that's not the whole story. There's cost and a lot of other factors to consider, but it's significant. And why is this significant in terms of what could be done in going further in silicon carbide devices? So we've kind of hinted at this in the blog, and we'll go into this a little bit more today. What if you could have a superjunction silicon carbide MOSFET, and if you could make it, there's a lot of ifs to get down that path, but if you could make it cost effectively on a mass production scale, you could really significantly lower that device specific on resistance even further. Difficult to put an exact figure on it, but 2 to 3 times, potentially even more. And with the impact silicon carbide is already having in the market, this is very, very attractive. And in particular, in the market that everybody's after, the automotive market. So I'll dive into these figures a bit more, and we can discuss them. So the one that everyone always jumps to is specific on resistance. Now, it's not everything, and there's a lot of caveats to be had, but it's kind of a useful general metric to compare, from a conduction standpoint, where these devices are at. So you'll see this latest ROHM device we've looked at. It is the lowest specific on resistance device we've seen so far, but there's not much in it between that and the other leading devices in the market. I mean, Peter, what do you think in terms of how it stacks up?
The ROHM Gen 4 is a bit of a step forwards. Just to add to what you were saying before, having the lowest specific on resistance is what we're driving for as device designers. We reduce that specific on resistance as far as we can. We're shrinking our die down as much as we can, and that's actually helping our switching losses. You know, the capacitance of a smaller chip is less, and so our switching is faster, and we save energy in switching. So we're trying to drive that down as much as we can, as well as saying that the smaller the chip gets, the cheaper it gets. So there's a gain in terms of both efficiency and economics by driving that specific on resistance down as far as we can. In terms of that ROHM Gen 4, in a like-for-like comparison with the best planar device out there, and you've got a couple there in terms of the Wolfspeed and the ST devices, it's about 40% better than the Wolfspeed device when you look at when you take out the difference that you've got in this table from on resistance. So it's quite a big step forwards. So these values of specific on resistance we have here should be kept in context with the on resistance of the device. So where you have them at the same on resistance, you'd see about a 40% gain for the ROHM device, and that's a real advantage to having that trench structure that we'll have a look at later. So yeah, I think it's the real, for me, it's I'd say it's the first trench device I've got very excited about, to say that, you know, this feels like a real step forward, that trench is being utilized to the maximum and really shrinking down the die and also protecting the gate, as we'll see later on. So it's a reliable device as well as a small device.
Absolutely. And yeah, these figures, there are caveats to them as well. Obviously, they're taken at different gate bias. Different manufacturers recommend different gate drive conditions, as you'll see at the bottom of the table. And there's a lot of other factors to consider. I mean, something that trench MOSFET manufacturers always make a point of, they're the only ones that provide 0 volts device turnoff instead of needing negative gate bias for turnoff. There's a gate charge to consider, switching, robustness, and obviously there's a sliding scale in terms of the chip size, the chip area, and how things like the gate charge scale. Another thing that's, before we move on and dive deeper into the devices themselves, it's worth noting the top row of that table and the actual structures. So we've touched on that a little bit. onsemi, Wolfspeed, and ST have a planar polysilicon gate structure. Infineon use trench, and ROHM have their so-called double trench design. United Silicon Carbide is a little bit different. They use a cascode connected JFET, and they have even better on resistance, specific on resistance still, but again, there's kind of conditions to be kept in mind with that.